Okay, before we start the next lesson, just going to do some Anki and go over what we did last session. So what is a symbol table? It's a data structure that contains the mappings from the lexical analysis phase. Basically it's a table where you can use a token to look up the token like attributes information. Yep, pretty good. What is meant by the back end of a compiler? So that's anything that's machine dependent, so like optimizing and translating for specific architectures. Good. Compilers, what is meant by the front end of a compiler? Anything that is machine independent, so anything that can be generalized and applied and before you need to make it machine specific. So the lexical analysis phase, syntactic analysis, semantic analysis, some intermediate code representation, those sorts of phases. What is semantic analysis? So it's the second phase of compiling. It's where it takes the tokens, which were gathered from the lexical analysis phase, and it turns it into essentially an abstract syntax tree. So it makes sure the actually, I'm completely wrong. It's the third step in compiling. So it takes the abstract syntax tree, does type checking, and checks the correctness of the program. That's okay, that happens. We'll just do that again. Compilers was code generation. Code generation is essentially the fourth step in compiling. It's where you take the result of the semantic analysis, and you create an intermediate representation of the code. This can also be done in later phases in the back end, where it can be you can turn it into like assembly, machine specific assembly. This phase can also create like a control flow graph, which is another intermediate representation. Yep, good. What are some of the basic ways the compiler optimizes code? The most important thing is register allocation, which is basically where you assign variables to registers. And the second thing is using more advanced or more efficient machine instructions to avoid branching. Good. What is the advantage of having the compiler output assembly language instead of machine language? Firstly, assembly language is easy to output, and it's easier to debug. Way easier to debug than machine language. What is lexical analysis? The first phase of compilation, where you take the source code or the source input stream, and you turn that into lexemes, and you pick out the lexemes, you turn those into tokens, pretty much. You send that off to the syntactic analyzer or the parser. What is semantic analysis? So this is language correctness checking. So you take the result from the parser or the syntactic analysis phase. Then you do some type checking on it, and you check for semantic correctness. Yeah, so make sure it's semantically correct, essentially. Good. And then from then on, you would move on to code generation. Regex. What does this match? So the A concatenation of A in the empty string is the set containing A. Yeah. Good. What does this match? A or B, the set containing A and B. Well, that was easy, so we'll say easy. What does this match? So that is the clean closure of R, or the language of R. So that would be the empty set, a set containing the empty string, then the language of R, then the language of R concatenated with the language of R, the language of R concatenated with the language of R concatenated with the language of R, so on and so forth. Easy. What does this match? It's a clean closure of A and B. A concatenated with B, so it would be the set. Actually, no, that's not it. So it's A concatenated with the clean closure of B. So we would have this would match the set containing A, then AB, then A, B, 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 etc. So it's A concatenated with 0 or more B's. Pretty sure I must have written this down wrong. That's got to be right? Like A concatenated with B. I'm just gonna check that. Maybe I'm completely misremembering. So that should not match the empty string. I don't know how you represent the empty string. Should not match, but it should match A. Should match AB. Should match A, B, 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 B. But it should not match the empty string. How do you represent that? Yeah, so I think I need to update that. There we go. Easy. What does this match? Question mark. Oh, that's a good question. Ooh, I totally forget. Gonna have to redo this. So the language of R or the empty string. So it's the language of R or the empty string. Okay, so it's R or nothing. Got it. What does this match? Matches the set containing A, B, and C. Good. Should have said easy. That's all right. What does this match? The set containing anything but A, B, and C. What What does this match? The dot represents any character except the new line character. That matches any character. Where's Alexa generator? Ooh, okay. So Alexa generator is a program that you essentially you give it regular expressions as a language definition. So you define a language using regular expressions, and you give that to the Alexa generator, and it outputs Alexa program for you. Takes a regis specification as input, yep, and outputs code implementing Alexa that breaks its input into tokens. Good. That wasn't easy, but it was good. Regex, what does this match? R question mark. It matches the language of R or the empty string. Good. What is this called? The clean closure. Easy. What is this called? The positive closure of L. What does this match? This one was easy. So a set containing A and the empty string. Oh, I read that wrong. So it's A concatenated with the empty string is just A. Let's do that again. What does this match? The set containing A, B, or C. A, B, and C, sorry. Yep. What does this match? A concatenated with the empty string is a set containing A. What is Alexa generator? It's a program that takes a regular expression language specification as input, and it outputs a lexical analysis program that breaks source code into tokens according to the specification you've given it. Good. What does this match? R question mark matches the language of R or the empty string. A set containing the language of R and the empty string, that is. What does this match? A concatenated with the empty string is a set containing A, and that's it. Cool. All right. Sync that up. So cool. So we're now on lecture 3, which is automating lexical analysis. So, automating lexical analysis. And notice the homework is out at this point in the course. So after this lecture, we have homework. The homework isn't due until lesson 6. So I'm gonna have a look at it, see if it actually requires the stuff in lessons 4, 5, and 6. If it does, then obviously we'll wait a bit to do it, but we'll probably attempt it after this video. We'll see how it goes. Let's do this. Automating lexical analysis. Hell yeah. Automating lexical analysis. Alexa generator converts a lexical specification consisting of a list of regular expressions and corresponding actions into code that breaks the input into tokens. Yep. This lecture we examine how this convention works. We can think of a lexical specification as a big regular expression. Language of R, union of the language of R1 and the language of R2, all the way up to the language of Rn, where each R is the description of each token. Okay. A Lexical generator works by converting this regular expression into a deterministic finite automaton. This is done in a couple of steps. First, the regular expression is converted into a non-deterministic finite automaton. The non-deterministic finite automaton is converted into a deterministic finite automaton, which then becomes the basis for a table-driven lexer. I'm not sure what a table-driven lexer is. Going to going to quickly consult ChatGPT. A table-driven lexer is an analyzer or scanner used in the construction of a compiler. It operates based on tables or data structures that define lexical analysis rules for a programming language. These tables specify how to recognize and categorize tokens in the input source code. Does it just mean the symbol table? No. Transition table contains information about the transitions from one state to another based on the input characters. It is often implemented as a finite automaton, such as a DFA or a non-deterministic or an NFA. The transition table specifies which state to transition to when a particular character is encountered. Gotcha. Cool. Cool. So, right. So it's an NFA and then it's a DFA, which is more abstract, and then it becomes, then you actually implement the DFA as a table-driven lexer. Okay. Recall that a DFA is an abstract machine. The machine reads an input stream of symbols. The symbols are in the alphabet sigma, where sigma is the alphabet of the DFA. It has a finite set of states, Q sub I. There is a distinguished initial state, Q sub 0, in which the machine begins reading its input. Makes sense? As the machine reads each symbol, it changes its state according to a transition function delta. On reading symbol X in state Q, it changes to the new state Q prime, where Q prime is equal to delta of Q and X. Makes sense? So we're sitting in the state Q. To get to Q prime, we apply the transition function on the state and the symbol. Make sense? It has a set of final or accept states F. The machine accepts the input if it arrives at the end of the input in a final state. Q, if the state is in the set of final or accept states. Makes sense? A DFA can be drawn as a labeled graph in which states are nodes. The individual state Q sub 0 is indicated by an incoming edge from outside. Yep. Other edges are labeled with the corresponding input symbol. And final states in F are marked by nodes with double circles. Yep, that makes sense. For example, consider the following DFA, which accepts only odd numbers expressed in binary, corresponding to the regular expression. Alright, so this regular expression is 0 or more occurrences of 0 or 1, suffixed by a 1. So let's draw that out. Zero, union of 1, clean closure of that concatenated with 1 becomes, that is the set containing 1 you could have 0, 1. That's terrible. 1. You could have 1, 1. These don't look like ones. Yeah, and then you could have any combination of zeros and zeros and ones. Is that right? But it always has to be preceded. It always has to be suffixed by a 1. Let me double check that. I can't remember if this. So that specifically there is the set of 0 or 1. 0 and 1. Can that equal something like that? I can't remember. I'm going to have to check this. So we know it has to at least equal 1. It shouldn't match the empty string. We know it can equal 0, 1. We know it can equal 1, 1. We know it should always end with a 1, so can it equal 1, 0? That should not match. Did that just match? 0. Zero more occurrences of 0 or 1 should be concatenated with a 1. It should always be concatenated with a 1, right? Wait, that shouldn't match. Okay. I'm obviously interpreting this wrong. Let's ask ChatGPT. Yeah, ChatGPT says that shouldn't match, so why is this saying it does match? It should not match. 0, 1. No, that shouldn't match, right? Match information. Match 1. Group 1. No, that doesn't. That's right. But 1, 0. Why is that matching? Let's try another. Zero, 1. Clean. Closure of that. Concatenate with 1. Should match 0, 1. But should match 0, 0, 0, 0, 0, 1. 0, 0, 0, 1, 0, 1. Should not match 1, 0. Yeah, okay, it doesn't. Right. It's saying it doesn't match. It's just saying that that specifically matches. Right, okay. Just misunderstanding. All right. So let's try and decipher this DFA. So we start in this state. If the first letter is 0, we return to this state because we can't finish. I'm guessing this is what this means. If the next letter is 0, we can't finish. If the next letter is 1, we can finish. If the next letter is 1, we can still finish. It's still valid. If the next letter is 0, we have to return to the original state because we can't finish yet. We cannot finish if the string, if the next token is 0, sorry, if the next symbol is 0, we cannot finish. We cannot reach a finished state. If the next input token is 1, we can reach the final state. All right, that makes sense. We model illegal characters by adding a non-final error state to the DFA, which we typically do not bother to draw in such a diagram. Yeah, makes sense. So I get what they're saying. So you would have entry point. Here's our final state, and here's our error state. To get there, use any invalid character. Makes sense. Invalid symbol. That's how you get there. Makes sense. And to get to the final state, you obviously use valid symbols. Do these have keybinds? No. Every state has transitions to the error state on every symbol that cannot lead to a final state. Therefore, delta is a total function. What do they mean by total function? I'm going to ask ChatGPT. In the context of automata theory and formal languages, a total function refers to a function that is defined for every possible input or argument. A function that is defined for every possible input or argument. In other words, a total function is one where there are no undefined or missing mappings. There are no undefined or missing mappings between inputs and outputs. Every possible input has a well-defined corresponding output. In the passage you provided, they are referring to the transition function, usually denoted as delta, of a DFA. The DFA's transition function defines the state transitions based on the current state and the input symbol. When they say delta is a total function, it means that for every state in the DFA, there are defined transitions for every possible input symbol, including those that should lead to an error state. This ensures that the DFA can handle all possible input symbols without encountering undefined. Okay. For instance, if a DFA is designed to recognize a specific language and encounters an input symbol that does not belong to that language, the transition function should still define where to go. Okay, so delta always knows where to go, no matter what happens. No matter what the input symbol is, delta always knows where to go. We can describe the transition function delta as a table, which hints at how we might implement the DFA. So if we, makes sense. If the input is, if the token read is 0, we go to state, and we're already currently at state q sub 0, then we stay in state q sub 0. If the token is 0 and we are at q sub 1, we go back to q sub 0. If the input is 1, we always go to q sub 1. Pseudocode for a DFA that reads an input of length n, where input I is the ith input character. Pseudocode for a DFA that reads an input of length n, where input I is the ith input character, is simple and efficient. It is a loop that simply reads the appropriate table entry for each input character and updates the state accordingly. So we start at I, start at q sub 0, while I is less than n, or the input length. Q equals delta function on the current state and the current red symbol. Then we move to the next symbol. If Q, so if we end up in a final state, return accept, and then return val. Now the question is, how to obtain the table delta? How to obtain the table delta from a regular expression? Right, yes, that is the question. How do you define that function? The first step is to convert the regular expression into a non-deterministic finite automaton. An NFA differs from a DFA in that each state can transition to 0 or more other states on each input symbol. And a state can also transition to others without reading a symbol. Okay, in the diagram representation, multiple exiting edges can be labeled with the same symbol. Edges corresponding to not reading a symbol are labeled with epsilon. Edges corresponding to not reading a symbol are labeled with epsilon, meaning the empty string, I guess. So if we're in this state, we don't read a symbol, or we read an empty symbol potentially. We can either go to A or B. We can either go to one of these states. Then if we're up here, we read A. We move to this state. And we can potentially read, I'm guessing that this allows us to jump straight to a final state. I think. In the diagram representation, multiple existing edges can be labeled with the same symbol. Edges corresponding to not reading a symbol are labeled with epsilon. We write Q X arrow thingy Q prime to mean that the NFA can transition from Q to Q prime on symbol X. Okay, makes sense. So Q can go to Q prime on symbol X. Makes sense? For example, the following is an NFA. So if we're here, the next character read is B, or the next input symbol read is B. We can stay, we have to stay here. If it's C, we can either go to this end state, or we can go up to here, to this state. Yeah. The NFA accepts a given input stream if there is any way to reach a final state while reading the entire input. That is, it exhibits angelic non-determinism. The NFA accepts a given input stream if there is any way to reach a final state while reading the entire input. That is, it exhibits angelic non-determinism. We imagine that when it needs to make a choice, there is an infallible oracle telling it which transitions to take. If the machine above receives the input A, B, A, it can reach a final state by choosing the upper epsilon transition and staying within the top 3 states. Yep, so if we read the character ABA, well, the prefix of this is always the empty string. So we prefix, so we can start up here. Essentially, we come in here, we read the empty string, and we start up here. We assume we're up here. We read A, we read B, we can choose to loop here, and then we read A again, we're at a final state. So that works. It can reach a final state by choosing the upper epsilon transition, staying with the top 3 states. Therefore, the machine accepts this input. It can also accept A, B, C by choosing the lower B transition. The lower B transition, so A, B, C, makes sense. The machine does not accept AC, however, because there's no way to reach a final state. Yeah, A, and if you hit C here, you get nothing. Challenge, can you write a regular expression that describes exactly the strings that this NFA accepts? Okay, so let's draw this out. How do you... Let's redo that. Okay, so this thing either starts with A or B. So it either starts with A or B. Then from B, we can always take so from here we can do 3 things. We can end by reading A. Here we can end by reading C. So it should always be concatenated with A or C at the end, right? That's what I'm thinking. In this state, we can do a B transition. So we can have any number of B's. Down here, we can have any number of B's. We can have 0 or any number of B's. So we have to, so this must include the clean closure of B. Then if we do a C, if we do a C, okay, so if we're here, we do C, we can't reach an end state. If we do C, we cannot reach an end state. Oh, what do we do here? If we do B, we can do any number of B's. It doesn't matter how many B's we do. We can do 0 or many. Looks like we can only do a C. We can only do C after we've done B. We can only do C after we've done B. How do we represent that? So to do C only after you've done B. B, C, right? Wait. I'm gonna see if there's an NFA builder online. So NFA from regex. But regex to NFA. Let's see if you can actually do that. Let's see if this works. So we had A or B concatenated with any number of B's, 0 or more, and then A or C. You have to concatenate that with A or C. See what that looks like. Is this working anymore? Guess not. Just trying to find something that does it for me so I can just visualize it. Yeah, I'm totally don't know what to do for this last one. So just gonna type this in ChatGPT, see what happens. Here's a textual representation. Starting state Q0. Transition on A or B to state Q1, transition on B, state Q2. Either I'm completely wrong or it is. Maybe a bit of both. Can you write exactly the strings that the Santa Fe accepts? It does accept C, but only after B. Something like C question mark. I think. Let's try that again. Let's try that. See if ChatGPT understands that. Let's type that in and see what happens. A or B. Sorry, A or B. Then the clean closure of B, and then 0 or 1 C. Oh, wait. Oh, man. A or C. So, it says this takes ABA. Match 1 ABA. It says it also it doesn't take AC. So it should just take ABC. That works. ACC should not match, right? Yeah, I'm totally wrong here. Tough one. I would assume it has to end on an A or an end on a C. It has to start with an A or start with a B. It can do any number of Bs in between those, and can do any number of C's, but only after a B. Oh, okay. So it can do any number of BC. So that would be any number of B, C. Pretty whack, but that's how I see it anyway. So any number of B, C, So AC shouldn't match, right? So AC. Damn it. It does match. So A, right. If it starts with A, you can't do C. So how do you prevent that? So, okay, so this string B, C, B, C is valid. The string A, B, C is valid. So C can come after a B. Makes sense. C can only come after a B. Or BC. So now AC doesn't match, but ABC should. Then let's see if BC should match. BC should match. So we should be able to go BC. If I get rid of this, potentially, that might be the answer. But then you'd have to have only BCs, I think. So if I got rid of that, AC won't work. BC should. ABC should. BC should still work though. Oh, we're close. I think we're close. So That's the wrong. That's wrong as well. So we can start with A or B. Start with A or B, right? Then we can have any number of B's. It doesn't matter how many we want. We can have C's, but they must follow a B. Any number of B's and any number of BC's. But then that cuts out the first BC. What if we use any number of B's here, cut them there, and finally a number of B's, then if I do that, that doesn't help, does it? So that way BC works, then BC C should break, yep. BC B should work. Oh, B should be any number of B's, right? Oh. Because that should accept BCB. B, C, B. Oh, no, it needs B, C, B, C. No, that makes sense, right? So B, C, B, C, that should work. Okay. We're getting somewhere. B, C, B, B, C should work. B, C, B, B, C, that should work. Awesome. Wait. Wait, why is that? Why is that two separates there? Should this be BC's or a number of B's, right? Is that working? I can't tell. Let's try a different one. Let's try A, B, B, C, A. A, B, B, C, A. There's got to be a better way to handle these C's, right? Alright, I have one more crack at this and then I'll move on. So we can start with A or B. That's wrong, because you can't start with zero B's, right? Wait. Because A or the clean closure of B would be a set containing A, the empty string B, 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 and so on. So that can't be right. So that has to go. We have to start with A or B. Then, from there, if we do a C, it has to be following a B. So we could also potentially do, and it has to, I know it has to end with A or C. It's got to end with A or C. Could have any number of B's in between. But if we do a C, it has to be after a B. If we're at A, we cannot do C. Cannot do C whatsoever. So wait, can we specify something like can we do something like not C? That's any character except C. That's too vague. Regex. Got to ask the chat GPT. Here we go. To match a C only when it follows a B, you can use a positive look-behind assertion in your regular expression. In many regex engines, look-behind assertions allow you to specify a condition that must be met. So, it's a positive look-behind assertion that checks if there is a B immediately preceding the C. Alright, plug that in, see what happens. I think, I hope I've even interpreted it correctly in the first place. So, any number of B's followed by actually, it should go here, right? I think. Question mark, less than or equal to B, C, then any number of B's, and this should also be any number of B's here. And we should end on a C. If we do a C, we have to do we have to do a B to get back to A? Ah, fuck. So let's say we do C. From C we can do an A. From here we can only do an A. And from here we can only do a C to finish it off. So to end on C, we must check that we've done a B. And to end on A, we must check that we've done an A or a B. An A or B or a C. An A or B or C. Oh, oh man. Yeah, I totally screwed this up. Yeah, I'm completely. Moving on. Embarrassing. The NFA accepts a given input stream if there is any way to reach final state. That is, exhibits angelic non-determinism. The Does not accept AC because you can't get to, yeah. Doesn't accept AC, but it should accept BC. Should accept ABC. Would that be a clean closure? That's getting better. And then ABSC. Oh, hang on. To finish on A, we have to have done an A or a B or a C. To finish on C, we have to have done a B. Oh, did I get it? This may be it. This may be it. Let's do another test. So to finish on, okay, so we can go. Let's say, let's try B. So this should be valid. We should say A. A should be valid. A, B, B, C should be valid. A, B, C, B, C, B, C, A should be valid. Why did that not join? We're getting close. BCA should be valid. So let's try something that it's not valid. So BCC should not be valid. Nice. BBC valid. A, B, C should be invalid, right? A, B, C. Ah, damn it. Oh no, ABC is valid. ABC is totally valid. AB should be invalid. Nice. A. ABB. ABB should be invalid. ABB. Hell yeah. Then BCB should be invalid. BCB. Wait, because BC is valid. So yeah, BCB should not be valid. Makes sense. Hell yeah. I think I did it. I think I cracked that shit. Let's go. Let's go. So that's cool. Spent more time on that than I wanted to, but we got there. So, RE, regular expression to NFA. We now see how to translate a regular expression to an equivalent NFA by induction on the structure of the regular expression. That is, given that we know how to convert the sub-expressions of a regular expression, we show how to use the NFAs produced by those translations to produce the NFA for the full expression. In each case, the result of translating a regular expression will be an NFA with a single except state. The result of translating a regular expression will be an NFA with a single except state, which some represent with the following diagram. In which the squiggly dashed arrow and surrounding oval represents some additional nodes and edges that are part of the NFA. Okay? Let us write R to mean the translation of a regular expression R to an NFA that accepts exactly the language of R. Okay? So this means translating the regular expression R into an NFA. The special double brackets are known as Oxford brackets and are used to express translations. We define the translation recursively as follows. By induction on the size of the expression R. We define the translation recursively as follows by induction on the size of the expression R. Okay, so the empty string. We get to the empty string in one jump. So from translation of the regular expression of A into an NFA looks like this. Simple. The translation of the regular expression R1, R2 looks like this. So R1, then the empty string gets us to R2, and we finally end at the end of R2. So it's the concatenation of R1 and R2. R1 or R2, so the union of R1 and R2. We can start in R1 or R2, and we can end at the end of R1 or R2. And we don't have to, and they don't intersect. So the translation of the regular expression R, the clean closure of R, we start here. From the empty string, we can finish. So it can either be the empty string or it can be the beginning of R to the end of R, and we can do it again. We can concatenate it with R as many times as we want, and we can finally end with the empty string. By working bottom up, we can use these translations to construct an NFA for any regular expression. For example, the odd number regular expression above translates to the following NFA, which clearly accepts the same strings. The unlabeled edges in the diagram are epsilon transitions, empty string transitions. The states in this diagram are labeled with letter names for later use. So we can start with any empty string, empty string, empty string. We can go to, we can read in 0 or 1. After we read in 0, We can go to any empty string, empty string, empty string. From 0 we can get to 1. From 1 we can also get to 1. Yes. And from here we should also be able to get back to 0. Sorry, we should be able to get back to state B as well, I think, but I don't know, I'm tired. I'm going to take a break and pick this up soon. Alright, continuing on from the last session. So, NFA to DFA. Although an NFA clearly can do anything a DFA can, the reverse is also true. We can convert an arbitrary NFA into a DFA, though the DFA may in general be exponentially larger than the NFA. The intuition is that we can make a DFA that simulates all possible executions of the NFA. Fair enough. At any given point in the input stream, the NFA could be in some set of states. For each set of states, the NFA could be in during its execution. We create a state in the DFA. Alright? The final states of this DFA will be the states that include some final state from the NFA. The final states of this DFA will be the states that include some final state from the NFA. Since being in that DFA state means that the NFA could have reached a final state. Since empty strings transitions can be taken at any time, it is useful to have the concept of the empty string closure of an NFA state Q. Empty string closure of an NFA state Q. It is the set of all states reachable from Q using 0 or more empty state transitions. Set of all states reachable from Q using 0 or more empty string transitions. Similarly, we can take the empty string closure of a set of states by defining all states reachable from any state in the set using only empty string transitions. For example, in the odd number NFA above, the empty string closure of F is the set empty string closure F FGA BDH. So the empty string closure of F is the set F to G, F to A, F to B, so you can get there through A, I'm guessing. Wait, D and H. Huh? So if we go from F to A, we can then get to B and D. If we go from F to G, we can then get to H, but we can. Why do we add the second jump? The empty string closure of EJ is the empty string closure of E unioned with the empty string closure of J. So that is, so from E to F, to A, because we can go from F to A, then B, we can go to B, we can go to D, we can go to G, we can go to H, And well, from J we can only go to J, right? I'm not sure why we do a second jump. Let's see if that, let's keep reading, see if it makes it any more. Now let's construct the corresponding DFA. Initial state of the DFA is the empty string closure of the start state of the NFA. Okay. Using capital Q to denote DFA states, that means Q0 is the empty string closure of capital Q0 is the empty string closure of Q0 from each DFA state Q. From each DFA state Q, we determine the set of states reachable in the NFA by finding for each possibly active an empty state closed set of states. What is a set of states that can be reached by following a single input symbol? Hang on, slow down. From each DFA state Q, we determine the set of states reachable in the NFA by finding for each possibly active set of states. What is a set of states that can be reached? By following a single input symbol from any of the states in the set. In general, multiple transitions may be possible, in which case all the reached states and their empty string closures, are in the reached state. In other words, the DFA transition on input X from a state Q is defined as follows. Delta of state Q and input X equals the empty string closure I'm going to need to see an example of this. To perform the conversion, we apply this step repeatedly for every DFA state and every input symbol until no new DFA states are constructed. Okay. In our example NFA, the initial state of the resulting DFA is the empty string closure of the start state of the NFA. That is the empty string closure of the set containing S equals S, A, B, D, G, H. From that set of states, we can make a transition on either 0 or 1. In our example NFA, we start here. From that set of states, we can make a transition on either 0 or 1. A transition on 0 can only happen from state B to state C. So the DFA state reached is the empty string closure of C from either of these two DFA states. We can transition on 1 to reach states E and G. So the final DFA state is the empty string closure of the state of E, of the set of states E and J. The full DFA looks as follows. Note that there will be a non-general final error state, capturing the case in which no NFA state is reachable using the input, though this state is not reachable for this particular example unless the alphabet includes some symbols other than 0 and 1. Okay, this is a step up, so So the first thing I need to flesh out my understanding of is the empty string closure. The book also says the empty set equals the clean closure of the empty set equals the set of empty string, set containing empty string, but since the empty set clean star in mathematical logic is a unary operation either on sets of strings or on sets of symbols or characters. Why can I not find more information on that? Alright, I'm gonna have to read this again. Although an NFA clearly can do anything a DFA can, the reverse is true. We can convert an arbitrary NFA into a DFA. The intuition is that we make a DFA that simulates all possible executions of the NFA. We make a DFA that simulates all possible executions of the NFA. At any given point in the input stream, the NFA could be in some set of states. For each set of states the NFA could be in during its execution, we create a state in the DFA. The final states of this DFA will be the states that include some final states of this DFA will be the states that include some final state from the NFA. Since being in that DFA state means that the NFA could have reached a final state. Since empty string transitions can be taken at any time, it is useful to have the concept of the empty string closure of an NFA state Q. Okay, it is the set of all states reachable from Q using 0 or more empty string transitions. Similarly, we can take the empty string closure of a set of states by finding all states reachable from any state in the set using only. So, I see it. I see what I was doing wrong. Yep. So, the empty string closure of F is itself G and H. Why G and H? Because you can take an empty string from F to G, and then you can take an empty string transition from G to H. So you can do these at any time because they don't require actual input, whereas the transition from H to J requires an input. The transition from D to E requires an input. B to C requires an input. That's what okay. Cool. So from F to A, we can once again take the empty string from F to D. But we can't go from F to E because we would require a 1 symbol as the input. We can't go from F to C. We can't go from A to S. Okay, alright, that makes sense. That makes total sense. So, for example, in the odd number NFA above, the empty string closure of F is the set empty string closure of F equals F, G, A, B, D, H. The empty string closure of E and J is the empty string closure of E unioned with the empty string closure of J. So let's do E. So from E we can go to F, G, and H. We can go to A, D, and B. And from J we can just go to J. So in total, the empty string closure of E and J is A, B, D, E, F, G, H, and J. A, B, D. Wait a minute. Where am I? Here. A, B, D, E, and F, G, H, J. Cool. Now, let us construct the corresponding DFA. The initial state of the DFA is the empty string closure of the start state of the NFA. The start state is S. So, what would that look like? The empty string closure of the start state of the NFA would be, it would be S, A, B, D, let's say SAD B, and GH. SAD B and GH. SAD B and GH. Okay. Using capital Q to denote DFA states. That means Q0 equals the empty string closure of state Q0. From each DFA state, Q, we determine the set of states reachable in the NFA by finding for each possibly active and empty string closed set of states, what is the set of states that can be reached by following a single input symbol from any of the states in the set. Alright. I'm going to try and draw this out myself without really looking. In general, multiple transitions may be possible, in which case all the reach states and their empty string closures are in the reach state. In other words, the DFA transition on input X from a state Q is defined as follows. Transition from this state used through X is empty to the union of the empty string. So the empty string closure of the union of all the states in the set capital Q, where Q can be transitioned to Q prime through X. Okay, alright, okay. Okay, I'm going to try this myself just to solidify this. See how close we can get this. So, in our first DFA state, we're going to have S. That's a terrible font. Actually, no, it's terrible. They're all pretty terrible. S, A, B, D, GH. Just need to look up the definition again. From each DFA state Q, determine the set of states reached in the NFA. Finding for each possibly active set of states. What's the set of states that can be reached by following a single input symbol from any of the states in the set? From each DFA state Q, we determine the set of states reachable in the NFA by finding for each possibly active set of states. What is a set of states that can be reached by following a single input symbol from any of the states in the set? Okay. Alright, so what I think they're saying is there are two transitions possible. So from S, we can technically get to E, so using 1, we can get to E, wait, a single transition, a single input symbol. So, a single input symbol, where am I? So we can get 2. If 1 is our input symbol, we can get all the way to E, F, and G, and E, F, G, H. We can also get to G, H, and J. So I'm just going to add A, D, E. Then we can get from E we can get to F. Then we can also get to G, H, and J. That's just from S. Then from A, it's the same. From D, well, it's not the same, it's just less. So from A, we can only get to E, F, G, and H. So D, E, F, G, and H, which are already in the set. From B, we can't get anywhere. From D, we can only get to E, F, G, and H. From G, we can get to H and J. And from H, we can only get to J. So that should be correct. Then from using 0 as the input, we can only get to, from S, we can only get to A, B, C, F, G, H. A, B, C, F, G, H. Because we can't progress past H. Then from A, we can only get to B, C, F, G, H. B, C, F, G, H. From D, we can't get anywhere. From G, we can only get to H. It's in the set. From H, we can't get anywhere. So from here, we can do like a loop thing, but I'm not sure. Not sure where we go from here. Like, so say we get to one of these states. So we go from S to A. I may have misunderstood this. Alright, I'm going to keep reading. Oh no, yeah. We're finding for each possibly active and empty string closed set of states. What is a set of states that can be reached by finding a single input symbol from any of the states in the set? In general, multiple transitions may be possible, in which case all the reach states and their e-closures are in the reach state. In other words, to perform the conversion, we apply this step repeatedly for every DFA state and every input symbol until no new DFA states are constructed. In example, NFA, the initial state of the resulting DFA is the e-closure of the start state of the NFA. From that set of states, we can take a transition on either 0 or 1. From that set of states, we can take a transition on either 0 or 1. A transition on 0 can only happen from state B to state C. So the DFA state is reached is a closure from either of these two DFA states. We can transition on 1 to reach states E and G. So the final DFA state is a closure of E and J. So, alright, let's try and think about this. So, from these states, if we hit another 1, we hit another 1, we can go from A, we can go D, E, F, G, H. We can also go to B. Can we get to J? I don't think we can. Can we get to J? I don't think we can right there. But from D, just realizing that I probably forgot to add B in here. This should include B. Okay, so from B we can't get anywhere. I won't do that. I'm going to include B in here. From B we can't get anywhere. From D we can get to E, F, A, B, and D again. We can get to G and H. D, E, F, A. So I'm going to include A in there. B is in there. So GH, yep. From E we can get to F, A, B, D, and get back to itself, obviously. But we can also get to J from E. And it looks like we can get to... That pretty much finishes us off there. Oops, that was supposed to be a J. Okay, so is this the same as this? A, D, E, F, G, H, B, and J. So that is the same. That's why we can get rid of this. Get rid of all that. Taking a 1 just takes us to the state that's the same as what we already have. What about taking a 0? Let's try that one out. 0. From A, we can get 2. We can get to A, B, and D. We can get to C, F, back to A. We can also get to G and H. Then from D, can't get anywhere. From B, it's the same as from A. From F, we can get to A, B, D, C, back to on itself, obviously, and we can get to G, H. That's it. And it looks like it. So with a 0, we can with 0 we can never get to J by the looks of it. If we have 0 we cannot get to J. From this state anyway. So we take a 1. Oh, hang on. So from J. Oh, but from J, if we're in J, we can get to J. I think. Maybe we can't if there's no explicit. There's no explicit explanation of that. So yeah, there's no input 0 here, so we can't get to J. If we're in any of these states and we have 0, we can't get to J, I think. Also, this should include D. I forgot that. And now this is actually the same. These two are actually the same, so we can delete that. I think. I hope I'm right. And 0 will take us to that state. So from this state, if we take 0, we can get to, from A with 0, we can get to A, B, D. We can get to C, F, G, and H. From B with 0, we can get to ABD, we can get to CF, we can get to GH. From C, we can only get to, yep, the same thing. From F, pretty much the same thing. We can't get anywhere really. We can't get to J for sure. From G, we cannot get to J with a 0. H cannot get to a J with a 0. So, ABD, CFGH, ABD, CFGH is the same as itself. So we can delete it. Finally, what if we take a 1? From A, if we take a 1, we can get to A, B, D, E, F, G, H. From B, if we take a 1, we can't get anywhere. From D, if we take a 1, we can get to pretty much the same. So we can get to D, E, F, G, H, and A and B. From E, pretty much the same. From F, if we take a, sorry, that includes a J. From E, if we take a 1, we can get to J. And then the rest, if we take a 1, we can get to J. So it looks like this is the same as this. A, B, D, E, F, G, H, J. Alright, so if we take a 1, we can get to here. Fingers crossed that's correct. Let's have a look. Zero, 1. I think I did it like flipped. They have 0 up here, so which is CFA, BDGH, CFA, BDGH. Let's compare these side by side. Put you over there. Put you here. Move you here. Okay, so the first state is correct. Sabdgg. Then from 0, we can get to CFA BDGH. CFA BDGH. If we take a 0 from there, it circles back on itself. If we take a 1 from here, we move to the final state, which includes J. Right, so if the state includes one of the final states, you add your second circle by the looks of it. So let's go like here. Then if we take a 1 from the first state, I also forgot to do the entry arrow. If we take a 1, we can get to EFA BDGHJ. EFA BDGHJ. If we take a 1 from there, we circle back on ourselves. If we take a 0, we get down to this state. Boom. Almost nailed it. Just missed out on the final state and the entry arrow. Not bad. Got the gist of it. Alright. Whew. So, in general, the DFA generated by this procedure may have more states than necessary. According to the Myhill-Nerode theorem, there is a unique minimal DFA that accepts the same input as a given DFA. This minimal DFA may be found by merging together the reachable states of the original DFA that are equivalent to each other. If the DFA contains any states that cannot be reached from the start state via some input string, these unreachable states can simply be discarded immediately since they do not affect the accepted strings. The argument for minimality goes as follows. For any state, there is a set of strings that would be accepted if that state were the start state of the DFA. For reachable states, these strings must be suffixes of input strings. For reachable states, these strings must be suffixes of input strings accepted by the full DFA. For any reachable state in the DFA, there must be a state in the minimal DFA that accepts exactly the same input suffixes, since otherwise there is some input prefix that would reach the original state, on which the minimal DFA would behave differently. Therefore, if each distinct set of input suffixes that are accepted by some reachable original DFA state is represented by a single state in the output DFA, that output DFA must contain the minimum possible number of reachable states needed to accept the same language. This is why we can minimize the DFA by merging states that accept the same suffixes. What? To be more precise, two states, Q1 and Q2 of a DFA, are considered equivalent, right? When written Q1, Q2 roughly equals. If the machine, having reached either one of the two states by reading some input prefixes, accepts exactly the same remaining input suffixes. Wait. Two states, Q1 and Q2, are considered equivalent if the machine, having reached either one of the two states by reading some input prefixes, accepts exactly the same remaining input suffixes. If the machine accepts or rejects exactly the same input suffixes when starting from those two states, then merging them together into one state cannot change the strings. Right, that makes sense. Hence with this notion of equivalence, there is a unique equivalence relation associated with any given DFA, which tells us how to reduce the DFA to a minimal DFA in which no distinct states are equivalent. Okay. We can find the equivalent states by finding all the states that are not equivalent. Let us write Q1 is not equivalent to Q2 if merging states Q1 and Q2 would change the language accepted by the DFA. In this case, we say that Q1 and Q2 are distinguishable. If two states are distinguishable, there must be some string S that is accepted starting from one of the states but not from the other. Let us write S. Must be some string S that is accepted starting from one of the states but not from the other. Let's write the string. If the string S demonstrates that the states behave differently, with one state accepting S and the other rejecting it. Clearly states Q1 and Q2 are distinguishable if one of them is final and one of them is non-final. Since the former case, an empty input suffix is accepted and the latter is not. That is, the suffix empty string distinguishes these two states. We can express this idea as the following reasoning rule, which we will call Rule 1. Q1 is in the set F, Q1 is not in the final set, then Q1 and Q2 are not equivalent. Rule 1 lets us identify states that are distinguishable with an empty input suffix. To find states that can only be distinguished by longer input suffixes, we need another rule. The intuition behind this rule is that if two states are distinguishable only by a non-empty suffix, the intuition behind this rule is if two states are distinguishable only by a non-empty suffix of length n is greater than 0, following the first symbol x of that suffix from each of the two states must lead to states that are distinguishable by a suffix s of length n minus 1. That makes sense. So, yeah, if Q prime 1 and Q prime 2 are distinguishable, well, they're not equivalent, then Q1 and Q2 are not equivalent either. Okay, that makes sense. The idea is that on some input symbol x, the machine transitions from Q1 to Q prime and also from Q2 to Q prime. Since Q1 and Q1 prime and Q2 prime are distinguishable, there must be some string S on which one of them accepts and the other does not. Yeah, that makes sense. Therefore, the states Q1 and Q2 are distinguishable because one of them accepts the string and the other does not. Right, that makes sense. We can use these two rules to infer that two states are distinguishable if and only if they are distinguishable on some input suffix. This can be seen by induction on the length of the shortest suffix that distinguishes two states. Clearly, rule 1 identifies all pairs of states that are distinguished by the empty string. If two states are distinguished by a single... Wait. Clearly, rule 1 identifies all pairs of states that are distinguished by the empty string. Okay. If two states are distinguished by a single symbol string, we must be able to apply rule 2 once to obtain two states that are distinguished by the empty string, on which we can use rule 1. Inductively, if two states are distinguished by an n symbol string, we can apply rule 2 n times to obtain two states similarly distinguished by rule 1. Therefore, if we cannot use these rules to infer that two states are distinguishable, there is no suffix that distinguishes the states. They must be equivalent. If we simply apply the rules as many times as possible until no new pairs of states can be distinguished, we'll find all possible pairs that can be distinguished using these rules. States not distinguished by the rules are equivalent. Okay? So you can use these rules inductively, and we can use these two rules to infer that two states are distinguishable if and only if they are distinguishable on some input suffix. This can be seen by induction on the length of the shortest suffix that distinguishes two states. Right? Clearly, rule 1 identifies all pairs of states that are distinguished by the empty string. If two states are distinguished by a single symbol string, we must be able to apply rule 2 once to obtain two states that are distinguished by the empty string, on which we can use rule 1. Inductively, if two states are distinguished by an n symbol string, we can apply rule 2 n times to obtain two states similarly distinguished by rule 1. Therefore, we cannot use these rules to infer that two states are distinguishable. Therefore, if we cannot use these rules to infer that two states are distinguishable, there is no suffix that distinguishes the states. They must be equivalent. If we simply apply these rules as many times as possible, till no new pairs of states can be distinguished, we'll find all possible pairs that can be distinguished using these rules. States not distinguished by the rules are equivalent. states not distinguished by the rules are equivalent. Alright, I'll take your word for this. I would need to see this. I feel like I need to see this visually to really understand this. The algorithm keeps track of whether each pair of reachable states are distinguishable, starting from the supposition that they are indistinguishable. Okay? It marks all final and non-final pairs distinguishable using rule 1. It then applies rule 2, following similarly labelled edges backward from all distinguishable states to identify additional pairs of states that are distinguishable. Eventually, no more distinguishable pairs can be identified. For the odd number DFA, the result of this algorithm is as shown in the following table, which compares all three possible pairs of states. Note that a similar table of size C Q2 can be constructed for any possible number of states Q. Trying to understand this table here. So Q1 is indistinguishable from Q1, obviously. Q1 is distinguishable Q2 by the empty string, I think. Q0 is indistinguishable from Q1. But I guess because right, okay, yeah, okay, because from Q0, if you take a 0, you end up at Q1. From Q1, if you take a 0, you end up at Q1. From Q0, if you take a 1, you end up at Q2. From Q1, if you take a 1, you end up at Q2. Therefore, these two are equivalent. Okay. From Q0 to Q2, what does this mean? What does that mean? Alright, let's have a look. By rule 1, states Q0 and Q1 are both distinguishable from Q2 using the empty string as input as indicated by the empty string in the table. States Q1 and Q0 and Q1 are both distinguishable from Q2 using the empty string as input. Oh, okay, yeah, that makes sense. Yeah. Because if you give them the empty string, they cannot get to Q2. They have to go through one of these. That makes sense. Rule 2 cannot be applied to either of these pairs of distinguishable states. So all distinguishable pairs have already been identified. Since Q0 and Q1 are not distinguished by any input, they can be merged, giving us exactly the two-state DFA shown at the beginning of the notes. Ah, cool. Makes sense. Implemented naively, this algorithm is much slower than it needs to be. We can speed it up by observing that there is no need to try to apply rule 2 to a pair of states that are not known to be distinguishable. And further, once rule 2 has been applied to such a pair for a given input symbol, there is no reason to try again. No further states would be found distinguishable. Therefore, the algorithm can maintain a worklist queue containing a set of pairs of states that are distinguishable, but to which rule has not yet been applied. Suppose the number of states from 0 to q minus 1, and record distinguishability of states I and j, where I is less than j. Store whether state I is final in final I. Then we can simply construct the process and process the work list. Apply rule 1 for I in the state 0 to q, for j 0 to I. If the final I does not equal, so if it's, so if I is not in final or j is not in final, then they're distinguishable. Push that to a q. Well, q is not empty. Read from it. For A in the alphabet, I0 in the set of states, J0 in the set of states, delta state 0 from symbol A is equal to I. Delta state J0 from symbol A is equal to J. So if these are equal and the state I0 and state J0 are not equal, swap them. What? If they're not distinguishable, is it calling itself again? What's going on? If they're not distinguishable, then they are distinguishable. Okay. Gonna have to. I'm hoping this is like in the homework, so we can really just dig down to this and sort it out. This is a bit confusing, but that's all right. Constructing the work list takes at most big O of q squared time, and since the work list loop can only process each pair once, it also takes at most big O of q squared iterations, each of which takes big O of what is that? Big O of the sum of the alphabet. What the one runtime is therefore right? Yeah, each of which takes the length of the alphabet time. The runtime is therefore q squared times the length of the alphabet. Thus far, we've been considering how to build a DFA for a single regular expression. However, the lexical specification for a set of tokens has the form regular expression 1, regular expression 2, regular expression 1 union with regular expression 2, union with up to regular expression n, where we want to know not only what the token is, but also which of the n token types matched. Further, we want to implement the longest matching token rule while prioritizing the patterns regular expression I appropriately. We start by constructing an alternation NFA while keeping the final states distinct so they can be associated with the appropriate Lexa action. We start by constructing an alternation NFA while keeping the final states distinct so they can be associated with the appropriate Lexa action. Okay. Makes sense? We convert this NFA to a DFA but continue to mark each final state with the corresponding action. Wait. Convert this NFA to a DFA but continue to mark each final state with the corresponding action, where two different NFA final states are both part of the DFA state. The action chosen is the one with the higher priority according to the Lexa specification. When the Lexa hits an accepted state in the DFA, it remembers which accepted state was encountered and keeps reading ahead. It only stops when the DFA error state is reached, because this means that there is no way to read more symbols to build a longer token. At that point, the Lexa rewinds the state of the input back to the last final state and invokes the corresponding action using the symbols seen to that point. One way to implement this backtracking is to assume the input stream has an operation unread that lets us put a character back into the stream. To find the last final state, the Lexa keeps track of all the states it has seen by pushing them onto a stack. It might seem unnecessary, though harmless, to remember the non-final states seen along the way, but we'll use this for an optimization shortly. So we start at I. A selected state is Q. Start with Q0. Read ahead until stuck, while true. Input I equals read. Read from the file if input I is in the file, or the delta function of the state and the next character is an error, then we break. If the state is in the final state, we clear the stack. We push Q. then we progress to the next state by calling the delta function with the current state and the next character or the next input symbol, and we increase the I value, backtrack to the last final state. While the state is not final, if the stack is empty, throw an error. We pop the last state from the stack. We walk back the input, and we minus I. Finally, we return the input. Start. Return the input from the start to I minus 1. For most lexical specifications, this algorithm will be fairly efficient and take time linear in the number of characters on the input. However, in the worst case, this algorithm can be quadratic because of backtracking. Makes sense? Consider what happens when the lexical specification is ABC union with union with the clean closure of ABC and D. So we would have, so we have ABC or, wait. So we can have essentially any number of ABCs concatenated with a D. And the input is these n characters. The correct result is a sequence of ABC tokens, but for each token, the Lexa reads all the way to the end of the input to find out whether there is a D. Yeah. The algorithm above will backtrack n divided by 3 times in this case, making the time a big theta of n squared. It's possible to ensure that lexical analysis takes linear time using an algorithm due to Tom reps. It memoizes hopeless Lexa states. If during the backtracking phase some non-final state Q is encountered at position I, there is no reason to try finding a token again from that state and position. If during a backtracking phase some non-final state Q was encountered at position I, there is no reason to try finding a token again from that state and position. We add a memoization table hopeless state and the index to record such scanner states. Modify the algorithm above slightly to update and use this information. So if we're in a hopeless state at the current index in the file, we break and we move to backtracking. If so, while the current state is not final, we call hopeless. We set hopeless at the current state and index to true. Yeah, if stack is empty fail, qpop, start unreading. Cool. Yeah, so if we end up in a hopeless state, we ended up breaking. Cool. To avoid quadratic lexing. Cool. An example of lexing ABC, 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 ABC. The Lexa will read all the input to find the first token, but on the second and following tokens, it will not read past the tokens that make up each of the ABC tokens. But on the second and following tokens, it will not read past the tokens that make up each of the ABC tokens, since the corresponding states are known to be hopeless. all the input to find the first token, but on the second and following tokens, it would not read past the tokens that make up each of the ABC tokens, since the corresponding states are known to be hopeless. Okay. Finally, recognizing regular expressions without DFA construction. The instruction above is worthwhile for recognizing regular expressions in a compiler, since the token specification does not change. However, regular expressions are frequently used in other settings where pre-compilation into a DFA is not worth the cost. Unfortunately, common regular expression libraries, such as those relied upon by Java and Perl, take exponential time in the worst case, because they use backtracking to handle the alternation operator. A straightforward but effective way to recognize regular expressions with little pre-computation is to construct the NFA from the regular expression, and then to directly simulate the execution of the NFA. As each input symbol is processed, the set of possible NFA states is updated, lazily constructing the states of the unminimized DFA on an as-needed basis. That seems much better. Thus, no backtracking is necessary. It's even possible to memorize these constructed states, yielding speed up for some regular expressions. An alternative technique is to directly interpret the regular expression as the input is parsed. Using regular expression derivatives, an elegant technique due to Janis Brzozowski. The idea is that for any given regular expression R, an input symbol A, we can compute the regular expression that accepts the rest of the regular expression after symbol A has been consumed from the input. Given any regular expression R and an input symbol A, we can compute the regular expression that accepts the rest of the regular expression after symbol A has been consumed. Okay, alright. We can use the suggestive notation something AR to represent the regular expression that accepts the rest of R after consuming A. Using the error state to denote a regular expression that accepts no strings. Okay, so using this to denote a regular expression that accepts no strings, and using plus to denote alternation. The regular expression derivatives of the various constructs are as follows. So the regular expression that accepts this way, wait. We can compute the regular expression that accepts the rest of R after a symbol A has been consumed from the input. So after A has been consumed from the input, what in the comments, as the comments, okay, let's try and figure this out. So empty string functions like the constant 1. The derivative, so the derivative of A is the empty string. The derivative of a constant is 0. The derivative of a constant B is 0, where B does not equal A. The derivative of itself is the empty string. The derivative of the regular expression A on itself is the empty string. The derivative of A on the empty string is an error state, or a regular expression that accepts no strings. Derivative of A of the regular expression A on B is nothing. The derivative of A on R1 and R2 is the derivative of A concatenated with R1 plus the derivative of A concatenated with R2, just like ordinary differentiation. Shame I don't remember differentiation. I'm gonna have to learn that again for sure. Do a calculus course. The derivative of A on the clean closure of R is the derivative of A on R concatenated with the clean closure of R, like differentiating an exponential. Like differentiating a product. Okay, I definitely need to relearn calculus, but not right now. As the comments in the rightmost column point out, these equations closely mirror the usual mathematical notion of a derivative. One small point of divergence is the rule for concatenation. The function v of r is equal to the empty string if r accepts the empty string, and the regular expression that accepts no strings otherwise. Such functions show up in other generalized notions of differentiation. Regular expression derivatives also conveniently handle negation and intersection of regular expressions. Alright, so that was pretty hectic. The homework, I'm hoping, drills down into this a little bit more so that we can, like, this is the kind of thing where you need a lab class. You'd go to a lab and you'd ask your, like, the TAs, and they would flesh this out for you and really help you to understand this. I don't have that, so I'm hoping the homework is able to help me with that. So yeah, cool. That's that wrapped up. So I'm not sure. I'm gonna have a look at the homework. If I need to learn more, then I'll make another video of me doing the of me doing the next few lectures or whatever. But if I think I can tackle this homework now, I will in the next video. All right, thanks for watching.